Okay, welcome to the Simple Interest walkthrough, Simple Interest free class walkthrough. Today we are going to be going over how interest accumulates, right? So you've probably heard of interest before. It's something that has to do with investments, right? So when you go and you put your money in the bank, it doesn't stay constant, right? You actually earn money towards your account. And it's usually a small amount, right? So if you have, say, a 1% interest rate, it's going to be related to percentages, what we learned in class in our percentages unit, right? We're going to learn what that actually means, though. What a 1% interest rate or a 5% interest rate, what that actually means, right? There are different strategies or different, when someone says 1% interest, that could mean different things. And we're going to look at two different types of interest today. On my screen right here, I have the worksheet. I'm trying out this new technology here today. I have this screen that allows me to write in space like it's at a whiteboard in class. So we'll see how it works. Yeah, so let's try this out. On the worksheet, you have the definition for simple interest, right? Simple interest. Let's write this out together and talk about each component. Right? So I stands for the interest that you earn, right? This is the small amount of money that you'd earn on an overall investment. P stands for the principal. Principal. That's a fancy word. It's the amount of money that you have sitting in the bank, right? Where does this come from? I don't know why they call it principal, but it's just a word you'll hear thrown a lot around in investment circles. Finally, not finally, R stands for the rate at which you're earning interest, right? So if you're earning 1% interest, this would be that 1% expressed as a decimal, right? Remember, whenever you're doing calculations with percents, you have to convert into decimal form. And then finally, T is the amount of time that principal or that investment has been sitting in the bank, right? All three impact how much money you're going to earn. Right? This looks very simple. It's three numbers multiplied by together, right? And look what you can learn from this equation. If you have more money in the bank, more principal, you'll earn more interest, right? If P is bigger, I is bigger. If you have a higher interest rate, you also earn more money. That also makes sense, right? A 5% interest rate will earn you more money than a 1% interest rate. And finally, also important, the more time you let your money sit in the bank, the more money you'll earn, right? So the amount of money, the time it's sitting, and the rate all impact how much interest you earn, right? Okay, so let's try out. I guess we're not going to do that yet. Are we? Nope, we're not. Well, I'm going to talk about compound interest in a minute, so let's save that for later. I'm going to point out that most banks don't use simple interest. They use another scheme called compound interest. I'll save that explanation for later because it is a little more complex. So let's skip to number 2, right? If you invest $3,500 in a savings account that pays 4% simple interest, how much interest will you earn after 3 years, and what will the new balance be? Okay. So in this case, we're going to calculate how much interest we earn, I, and then we're going to calculate how much money we now have in the bank, right? So that's going to be the principal we originally had plus the interest that we've earned, right? So we're going to do this in 2 parts first. I'll show you a shortcut in a minute. Okay, so in this case, if you invest $3,500, right there, invest, that's the amount of money that you put in the bank, right? That's P, the principal. So in this case, I'll write this for number 2, we're doing problem 2. P equals 3,500. Okay, that's good. In a savings account that pays 4% simple interest, right? So that tells you your interest rate in this case. Whenever you see that percent, it's an interest rate. So I'm going to write that down. R equals 4%, which equals 4 hundredths, right? Or 0.04, right? 3 ways of writing the same thing. How much interest will you earn after 3 years? So they tell you the time, right? 3. It's always assumed, for the most part, that interest rates are given in as an annual interest rate, right? So when it says 4% simple interest, by default, you assume that's the interest you would earn in a one-year period, right? So now we have everything we need to calculate I. Remember, I is the total interest, which is a dollar amount that you would earn. So in this case, I equals 3,500 multiplied by our rate multiplied by time. Okay. Calculating that, let's pull up a calculator here. Let's see. 3,500 times 0.04 times 3, that gives us $420, right? $420. Okay, so after 1 year, well, not 1 year, sorry, 3 years, that was in the problem statement. After 3 years, we have earned an additional $420. That seems like a lot of money, right? That's money that is essentially free, right, for you, that you all earned just by having money sitting in the bank, okay? It took 3 years to earn it, right? That's not just money in your pocket. It takes a while for that to accumulate. And that could have changed if you had more money in the pocket originally, right? Now, that wasn't the final thing, though, right? That's the amount of interest we earned, but it says we want to know how much money, what the new balance will be. Balance is how much money do you have in the bank now, right? Well, in that case, we have to take the principal we originally had and add the interest to it. That would give us the new balance. We're going to use a new symbol for that, by the way. We're going to call that A. I don't know why they use A. I think it stands for annuity is what they usually do, but that's a different thing. But anyway, A is going to be the new amount. Maybe that's what we'll have it stand for, the amount, right? The old principal plus the interest gives us the new amount in the bank. And in this case, that equals 3,500 plus 420. And if you do that math, that ends up being 3,920. That's the new balance, the new amount in the bank. Now you can simplify this formula. They do it for you above. We have a formula for I, so we can substitute that back in. And we get A equals P plus PRT. P shows up in two places, so we can use parentheses, right? We can collect terms. P times 1, that's the same thing as P, right? Plus PRT. So I'm going to pull out the P from both sides here, and I'm left with a 1 plus RT, right? So what's the opposite of distributing? Collecting, right? I've collected terms. I've pulled out a P out of that equation, and this gives me a formula that I can use to directly calculate the amount of the bank. Now I don't have to do this as a two-step problem. I can solve it as a one-step problem. Sometimes you are interested in the interest and you want to do it separately, but sometimes you just want to go directly to the new amount you have in your bank. And now I can solve it as 3,500 multiplied by 1 plus the rate multiplied by time, right? So this gives me 3,500 times, this ends up multiplying out to 0.12, so I have 1.12 times 3,500. So if you plug that into your calculator, we should get the same thing. 1.12 times 3,500, that gives us 3,920. And I just realized that this screen isn't as wide. That's so irritating. I'm sorry. I need to draw a line so I know how far I can draw up. I'm so sorry. But the formula is on the board. Okay, let's try this one more time. Okay, but we solved problem 2. I'm going to draw a line so I know the max distance. This is my, there we go. Shouldn't draw above that. There we go. Okay. Problem 2, more practice. You borrow $6,000 from a loan shark. Okay. Now interest works the other way too, right? You can put money in the bank and earn interest, but if you take money out from a bank, you're going to be paying interest, right? This is the worst. And loan sharks, just so you know, they're taking advantage of people by using very high interest rates. That's what loan sharks do. So you don't want to take money from one of those dollar loan centers or things like that if you can at all avoid it. You borrow $6,000 from a loan shark. If you will owe $7,200 in 18 months, what simple interest rate are you paying, right? So they give you the amount you originally took out, $6,000, and the amount you end up paying, $7,200, as well as the time. So this problem is working backwards. We can still use our formula, A equals P times 1 plus RT. Notice that I'm going to be using the amount, the full amount version. That amount you owe, $7,200, that's the original principal plus the interest you've accumulated. So if you use the other formula, I equals PRT, you won't get the right answer, right? Because this is giving you just the interest that you accumulated, not the full amount, the original principal plus the interest, right? So we have to use this formula. Look what they've given you. They've given you the amount you owe at the end after interest has been accumulated. They give you the principal, the original amount that you took out, $6,000. They also give you the time you've invested, right? 18 months. Now you have to be careful. Everything is assumed to be an annual interest rate. We're given time in months. So let's do that step first, right? What is T? Well, T, we want it to be in years. So we have to take 18 months and convert it to years, right? And we know, using dimensional analysis, that there's 12 months in 1 year. Months cancel. 18 divided by 12 gives me 1.5, 1.5 years, right? Okay, so we know our time. We got that, check. We know our principal, right? P is equal to 6,000, and we know our annual, our amount that we earn at the end, not earn in this case, that we owe, 7,200. Okay, so we're working backwards in this case. We need to figure out the R value, right? So we're going to need to plug in some numbers and then solve for R, get R by itself, right? You could do this in symbols if you want. You could actually find an expression for R in terms of P, T, and A. That might be a little confusing though. I won't do that to you. So let's plug in numbers and see what we get. If I plug in A, I get 7,200 equals 6,000 times 1 plus R. Remember, we don't know what R is, so it has to stay like that, times T. And I'm going to put T first. T was 1.5, right? So I have 7,200 equals 6,000 multiplied by 1 plus 1.5R, right? Remember, you can't combine. You can't just add 1 to 1.5 because they're different things, right? Like stays with like, right? These are in units of R. These are in units of ones. So you can't add those to 2.5R, right? That would be a mistake. Okay. So what do we need to do? Well, let's simplify. Let's divide both sides by 6,000. I actually don't know what that is. 7,200 divided by 6,000. That gives us 1.2. So 1.2 equals, what's left after we divide by 6,000? 1 plus 1.5R. Okay, that's what we have. Subtract 1 from both sides. I get 0.2 equals 1.5R. Divide by 1.5. And we're left with our value of R. 0.2 divided by 1.5. That gives me R equals 0.133. I'll round to that many decimal places. If I convert that to a percent, remember if I multiply by 100, that gives me an interest rate of 13.3%. Now I hope you see how massive that is. Normally interest rates at banks, the amount of money you earn at a bank is anywhere between 0.5 percentage point to like maybe 5 if you're lucky. Like you don't get that much. So they're overcharging you. Like you're paying a ton of interest. In just a year and a half you have to pay an extra $1,200, right? So that's insane. So we solved the first problem. We learned how simple interest works, right? It's just a simple percentage, simple ratio, right? Now let's go to the next page. Let's talk about compound interest, okay? Now we're going to see where this difference arises from. One of the things that comes up with investments is how often your interest is calculated, right? So simple interest, your interest is just calculated over the full period, right? Over the full period that you earned, right? So if you earn interest over a 3-year period, the interest that you earn is evaluated at after that 3-year period and then added on at the very end, right? At the very end. But that doesn't seem a little fair, right? Because if your money's sitting in the bank, shouldn't you be earning interest on the interest that you earned, right? And this is what compounding does, right? So if I earn, let's say I have an investment that's sitting in a bank for 3 years. Well, what if I evaluate how much interest I earn at the 1-year mark? After 1 year, I add the interest I've earned so far onto my investment, and now I'm earning interest on the original principal plus the interest I earned over that year period. Remember, more money in the bank means more interest, right? So this compounding effect, earning interest on the interest, is advantageous to the person earning the money, right? That's the idea. So you want to get that interest into your account as soon as possible, right? So if you compound your interest on a yearly basis, you're earning more money than on a simple interest basis, right? If you compound your money on a monthly basis, now every time you earn interest every month, now it's added to your account and you'll earn even more money, right? So the smaller the interval for compounding, the more money you're actually earning on your investment, right? That's the idea. Now there is a formula for that, and it's actually not too complicated. It's very related to the simple interest formula, right? I'm actually going to derive it from the simple interest formula, okay? So, let's see. Let's say, well, let's write out the formula for simple interest, right? Here's the formula that we learned for simple interest, right? Now let's assume that instead of multiplying out time here, what we're going to do is we're just going to calculate, let's assume time is equal to 1, right? Because we're assuming we earn interest every single year. So let's assume t equals 1, right? Well, that means I'm just going to have 1 plus r in there, right? Okay. So this is going to be the amount of interest I earn in 1 year. Okay. That's the amount of interest in 1 year. The next thing I'm going to do is, well, let's assume after 1 year, I add that money to my account, and then I go another year, right? If I go another year, then I'd have something like this, right? So this would be the amount of interest I accumulate in 2 years. Well, I can re-express that, right? I can rewrite this form like this, right? 1 plus r times 1 plus r, well, I can use an exponent to help me that out, right? This would be the interest I earn in 2 years if my interest is compounded on a yearly basis. Now finally, I could follow that process for more years, right? It doesn't have to be 2 years. I could change that to 3 years. I could change it to 4 years. So I'm just going to write that. I'm going to call that n, right? So this is the formula for compound interest if my interest is earned on a yearly basis, right? That interest is added at the end of each year. But that's kind of arbitrary, right? It could be every 12 months, right, instead. And so what we do in this case is we specify a value called n. N is like the number of subunits in a year, right? So n for if your interest is compounded every month, n would be 12, right? And now I'm going to split the interest up into n tiny pieces. And then I'm going to multiply the time that it accumulates. Time at t is in years, multiplied by n, the number of years over which it accumulates. And I should use the same symbol here for that, n and n. So that's where that comes from. The compound interest formula isn't something you just have to memorize. It actually comes from the simple interest formula, right? We just had to change a few things, one step at a time, right? First we assumed interest is assumed every year, and then we broke up a year into n bits, right? Smaller bits. So that's where that comes from, okay? And we can use this formula the very same way we use the simple interest formula, all right? So let's try an example. Problem 4. If $21,000 is invested in an account, find the value of the investment at the end of 20 years if the interest is, and now they show different schemes, right? You can use this if you wanted to compare banks, right? Let's say a bank offers these 3 options. You could compare and find out which one is best for you. First, let's assume that, should we do the easy one first? Should we do simple interest, just to review that? Let's do C first, right? Let's assume we're earning simple interest, 8% annual interest over a 20-year period, right? In this case, we have to use our old formula, right? Okay, there's our original formula for simple. And here I'll write compound, just to remind us. Simple interest, straightforward. Totally review, we just barely did this, right? It looks like I'm off the board again. I'm so sorry. I'm going to draw another line for me to remind me not to do that. Okay, this is compound. This is simple. Okay. Let's identify what we have here. The principal was 21,000. The time is 20 years. Time in these calculations is always done in years, right? And the interest rate, I'm going to convert that directly to a decimal. It's 0.08, right? Those are the numbers I'll plug in. And now I get my amount at the end as 21,000 multiplied by 1 plus 20 times 0.08. Okay. Well, let's plug that in to our calculator. What's 20 times 0.08? 1.6. Add that to 1. So I have 21,000 times by 2.6, which equals 54,600. Now, simple interest by itself, that seems like a nice deal, right? Well, it took 20 years, but over 20 years our investment grew 2.6-fold, right? We have more than 2 times as much money we originally had over a 20-year period. But that was just simple interest, right? Let's try the same thing with compound interest, right? So A, we're going to be compounded on an annual basis. In this case, n just equals 1, right? If n equals 1, we're left with A equals P times 1 plus R to the T power, right? That's how we write compounded interest for an annual basis. In this case, let's plug our numbers in. 21,000 times by 1 plus 0.08 raised to the 20th power, right? So I can plug that in, 1.08. I'm going to raise that to the 20th power. Let's see how I do that. Do they have that here? Not on this calculator. Let's go to scientific. 1.08 raised to the 20th power. That gives me 4.66. So that is a lot bigger than the 2.6 factor we found before, right? My investment has grown 4.6-fold by using annual compounding. So I'm going to multiply that by 21,000, and now my investment is worth 97,810 cents. Now look at that. Compare those values. If you just earn simple interest, you're almost earning like half as much money, right? If you were just compounding on an annual basis. Remember why you're earning more money with compound interest? The money you earn each year now is also earning interest, right? That's the advantage of compound interest. Okay. Finally, let's look at 8% interest compounded quarterly. Quarterly means a quarter of a year, right? So a quarter of a year would be every 3 months. So in this case, how many quarters are in a full year? Well, there's 4. So we're going to plug in n equals 4 into our formula, right? So in this case, I'm going to plug that in. I'm going to get P, I could plug in these numbers, right? 21,000 multiplied by 1 plus our rate, 0.08, divided by 4, raised to the 4 multiplied by the 20th power. That 4 by the 20th power, you can think of how many quarters you've gone through in 20 years, right? In this case, that ends up being 80 years, right? So if I plug that in, I get 21,000 multiplied by 0.08 divided by 4 is 0.02, right? So 1.02 raised to the 80th power. 1.02 raised to the 80th power gives me 4.875, right? So this factor here is 4.875. And that gives me 102,384.22. So that actually got me over the $100,000 mark, right? So now you can compare the relative sizes of these. You earn an additional $5,000 if your interest is compounded on a quarterly basis, right? And you can kind of push this to extreme. What if your money was compounded on a daily basis or a second basis, right? You can earn more and more money. Okay. Let's see. How many more problems do we have here? Let's see. We did the compound. Now there is actually one more. I just walked you through the last part. There's one other thing called continuous interest. I guess I had one more to do, right? One more practice problem. Yeah. I'll do this last one. 5 and 6. I apologize. Let's do 5 and 6. 5 and 6 are going to be very similar to the ones we just did. Erase, erase, erase. Okay. Keep our formulas there. Let's read about, okay, problem 5. If $45,000 is invested into an account, find the value of the investment at the end of 15 months if the interest is 6% interest compounded daily, right? So you just have to identify all your items. P equals 45,000. T, the amount in years, right? We want to do this in years, remember. 15 months. What is that equivalent to? How many years is that? 15 divided by 12, that gives us 1.25 years. So that's what we plug in for T. That is probably the most confusing part. Remember, you always have to convert your T into years using this formula. And how often is our interest compounded? It's compounded daily. So how many days are there in a year? 365. So that's what we're going to use for our N value. Did they give us a rate? Yes. So if I convert that to a decimal, it's 0.06. So plugging all that in, 45,000 times by 1 plus the rate divided by n raised to the nt power, right? So 365 multiplied by 1.25. Okay. So let's calculate that. What do we get? This is going to be a little hard to keep track of all the components. So let's do this problem. 0.06 divided by 365, add 1 to that, and raise that to the, I want to make sure I do this appropriately. Raise that to the, I'm going to use parentheses to help me out. 365 multiplied by 1.25. Okay, so there's my term there. That ends up being at that whole exponent raised to a power is equal to 1.0779 about. And if I multiply that by 4,500, that gives me $48,504.49. Okay. I will point out, don't round this at all when you're doing math. You want to use the exact value because those dollars and cents do matter when you're doing that multiplication. So make sure you use the exact value from your calculator than using the rounded amount, right? Just a heads up. So there we go. That's how interest works. This one we earned less interest overall because we didn't invest it for as much time, right? Only 15 months. The previous problem was 20 years. So you can kind of get an idea of how important time is for these investments, right? Awesome. Okay, let's do another problem. We're going to skip the one. There's one for you to do on your own. You have to compound the same amount monthly. And problem 6 is on your own. Problem 7 is on your own. Let's go to the back page. There's one other thing. we're going to push compound interest to the extreme. What happens if our compounding period is continuous, right? Like not even a fraction of a second. Instantaneously, when you earn interest, it's automatically added to your principal and you get interest on that, right? Well, what we'd be doing is n would be set to infinity, essentially, right? Your compounding period would be infinitely small. So in this case, the formula would look like this. R divided by, that's the symbol for infinity, raised to the infinity t power, right? So you have an infinitely small value being raised to an infinitely large value. Now, we typically don't plug in infinity, right? There's a fancy math way of doing this. We would actually write this, the limit as n approaches infinity. I'm going to show you some technical math here. This is the technically correct way of writing this. And it turns out, something kind of fancy, this here approaches a single value, a steady value. If you look at the limit of this term, this ends up being a fancy number called e, and you raise that to the RT power. So if your interest is compounded continuously, your final formula is P equals, A equals P raised to the e to the RT power. Now e is a fancy number, and it is equal to 1 plus 1 over n raised to the n power when n approaches infinity, right? That's where that e comes from. It actually ends up being a steady value. You can plug it into your calculator if you want to know what e is exactly. So let me clear. Here's what e is. That's the exact value of e. E is equal to 2.718 about, right, if we round it. It's a very important constant. It's very similar to pi, right? Pi, if you know pi, 3.14159, it's a number that has infinite number of decimals that just goes on forever. E does the same thing. It's an irrational number. It's a very important one, and this is one of the contexts where e shows up. If you have continuous interest, e is your friend, right? It's going to give you the largest possible amount of money that you could theoretically earn from interest, right? So this is the compound interest to the extreme. You earn the most money with continuous interest, right? Okay, if you invest $21,000 into an account that pays 8% continuous interest, what will be the balance after 20 years? So this is building on that last problem. This is going to show us the maximum amount of money we could earn over a 20-year period with an 8% interest rate. Well, it's the same problem. 21,000, but in this case we're going to take e raised to the 20th power multiplied by 0.08. Okay? And that ends up giving, let's do that, 20 times 0.08, what is that? 1.6. So we're going to do e raised to the 1.6 power. E raised to the 1.6 power. Okay, so our final investment increases 4.95 fold. And that gives us 104,013.68. That's the max amount of money you could earn over 20 years with an 8% interest rate if it was compounded continuously. Remember, continuous means every single fraction of a second you are earning interest. Okay, awesome. Continuous interest. That is the end of that one. I've covered everything in that. Let me know if you have any questions, and I will see you in class.